Hey folks, so we're going to get started here with our talk. Thanks for joining us this morning. So we are a team that did work on use case 3, which is utility edge compute. In our case, we focused on edge compute on utility routers over cellular transport. And as we go forward in this talk, we're going to tell you about the use cases, why they're important, how they save utilities money. We're going to talk about the team members. We had a really diverse team that worked closely together for this. And then also this, we're going to give cards. There's a lot of other chances to talk about this topic with us at our booth or in the days to come. So brief run through the agenda. We're going to start with goals, talk a little bit about the team members and the different components that we contributed. And then we had 2 major test beds to prove out our work. The first was utility edge apps with grid simulation that was conducted at Eaton's laboratories. The second test bed focused on utility app transport over cellular, and that was done at Verizon, Nokia, and Ericsson, and then we'll finish up with our conclusions. So this presentation, some of the slides have quite a bit of detail. It's because it was meant to be something that you could read as a narrative as well, but I'll give the highlights here. So the basic point is edge compute is a way to add value add to existing components on your utility network. So the routers that we used to host the edge applications made by Eaton, they're existing routers and utility networks. They're managed by existing tools, and through software-only additions, you can add significant value to your grid. So the 4 things that we set out to prove were that by using edge compute, you can save money and add significant value to smart grid. The second is that transport over existing cellular is something that's we have a lot of confidence in, is very stable, so we characterize that. And then finally, that this solution scales gracefully. So it's not something that we just did onesie twosie, it can scale to large numbers of control points on the grid. And in future slides, I'm going to go through the team and the topology a little bit more. But just to give some context about where in the grid this work is really focused. So most of the edge apps are on feeders or out in the distribution automation space. So they're using the routers that we use today to connect our feeder controllers back to the control center. But on those routers, there's an ability to host containers that do additional functions. So in this example, we had an edge app communicating at a cap bank controller, at a voltage regulator controller, and a battery energy storage controller. Then we also had a edge application running on a substation router in the substation that served as a hub and a communication aggregator. The cellular transport is existing macro transport from providers like Verizon, and then private transport from both Verizon, Ericsson, and Nokia. And then lastly, within the control center, we used existing router and app management and orchestration functions. So in this example, it was Cisco SD-WAN and Cisco Field Network Director to manage the routers and also manage those applications. And the net result was, so the business case that we tackled in particular was, it was around communications with the EMS and set point updates to the controllers. So as the amount of DER starts to increase on the grid, and the volatility of optimized set points increases on the grid, it becomes tougher for EMS to update those controllers on a frequent enough basis. So the EMS can be something of a bottleneck, and the main point we were doing with these edge applications was to ease that bottleneck, push some of that decision making to optimize the controllers out to the edge, and that's what those applications did. And on the, let's see if this pointer works. So the 3 routers at the bottom were what we call our leaf nodes. So those are the routers that are out on the feeders, talking to the controllers in the field. The router in the center is our substation router, and then up in so the cloud was the cellular transport, and up in the control center are orchestration applications as well as the master, SCADA master, and the EMS. So the team, and a little bit of a closer look at the topology. So I'm from Cisco. I'm an engineer on a utility practice at Cisco, and the routers that were used to host the applications and do communications between those apps. Those are Cisco routers. Eaton is a partner of ours. Stuart Laval, who's here with us, is going to speak after me. His team built the applications that are being used to talk with the cap bank controller, with the voltage regulator, and with the battery energy storage controller, as well as the app that was the aggregator at the substation. Then you can see in the cellular transport layer, we worked with Verizon. We deployed routers with these apps at their site, doing private 5G, private 4G, as well as macro 5G. We went to Ericsson and Nokia's labs as well. So what we built up and what we're going to show you is an extensive network of routers that extended from New Jersey to Texas and Eaton in Pennsylvania that were communicating this app traffic. Oh, and the 3 use cases in particular. So Stuart's going to show you a video of our results of how these apps were used to improve volt-var optimization. So if you used EMS for improved set points for volt-var, you might have update times on the order of minutes. We did update times on the order of seconds, which translates to significant saving of energy. It could also translate to longer lifetime of your grid assets because they're running in a more optimized state. Stored energy optimization and situational awareness were the other major applications. Okay, so just wanted to call out the other members of the team. So I introduced Stuart. Diana Tatum from Verizon is going to speak as well. So she's the lead of the team at Verizon, and behind each of us was a great team of support at each of our companies. Ericsson, Kevin Linehan was our counterpart, so he hosted us and hosted our routers and apps at his labs in Plano. Mauricio Subieta hosted us in Coppell, Texas at his laboratories. And then finally, Richard Mueller of DT Energy is a close colleague of ours and of Stuart's, and we validated our grid simulation models as well as this topology with him and DT Energy. And he validated that this was a very sensible architecture and something that he's very interested in. So the 2 test beds that we're going to talk through, the first is in line with a real-time hardware-in-the-loop grid simulator. It's made by Typhoon. So that simulates grid states on feeders. That grid simulator was connected to those controllers, the cap bank controller, voltage regulator controller, and the battery energy storage controller, which were then connected to our routers, the Cisco routers hosting Eaton applications. And that's the first test bed. So we're going to walk you through those results. And then the second test bed was to take those concepts, shift them to sites where we could do transport over cellular, both private and macro cellular, show, measure key performance indicators about that cellular transport, and then also use orchestration and management techniques to demonstrate how this could be scaled gracefully to thousands of routers. So I'm going to start with just a fundamental concept of what do we mean with edge compute in this environment. So if you look on the left, that's a topology diagram of our software architecture on our routers or switches. So essentially, there's a hypervisor that can host multiple operating systems. On the left is our switching and routing and security operating system called IOSXE. But next to that is a hosting environment called IOX. And on that, we can run Docker, we can run Linux containers. Oh. And that is where the application is hosted, in this case, as a Docker container. So the Eaton application is a Docker container residing on these routers. And then on the right, we're looking at a management console. So Eaton loaded 2 different applications. One is for southbound communications, one for northbound communications. But that's a look at how you would load this Edge app. And there are multiple methods to do it, but that's one way to do it. Okay, with that, I'm going to pass it over to Stuart.
All right, thanks, Dan. So as Dan mentioned, so I'm with Eaton. I lead global engineering around distributed energy resources and grid automation. We're their partner on the kind of the grid automation applications. We have about 3 decades of experience not only delivering the apparatus and controls for grid automation, we also sell the distribution planning software, SIME, as well as we do feeder automation software, as well as volt-var control software, typically at the data center. And what we want to do is bring that expertise closer to the edge. And we realized that when you start having a multi-tiered system, it may look complicated, but actually with this edge compute capability and the interoperability of both network and data, we actually augment the existing systems. So it actually simplifies and is in a very non-invasive approach. So you can continue to operate your grid in the central fashion in the minutes world, but then you can supplement that at the edge near the controllers, whether it's distributed energy resources like a battery system, a capacitor bank or voltage regulator, to work together to pull off a distributed function. So when we say distributed, we mean decentralized and centralized, and we're augmenting in a brownfield strategy. So going back to what Dan said, a lot of utilities are implementing telecommunications infrastructure anyway for smart grid. We're now adding an additional layer to capitalize on that infrastructure so we can now add additional use case capabilities that were validated, like utilities such as Detroit Edison. And so if you look at this drawing, at the very top you have a traditional energy management system or SCADA system like a DMS. It usually speaks a legacy protocol like DNP3, typically a client server. And then at the edge you have your controllers like your capacitor banks, voltage regulators. The unique thing about this demo is now we're incorporating a battery energy storage system. At Eaton, we do sell these energy storage systems for commercial industrial markets. And as we know, grid tying them to the utility can have potential challenges. But with this demonstration, we can use a digital twin of the grid. We're using a real-time grid simulator to emulate what the actual physics of the grid would behave, and then incorporate that distributed energy resource system in a way that not only can tie safely and reliably, but can be optimized in a peer-to-peer fashion with the voltage regulators. As Dan mentioned, you can optimize them in a way that can even extend the life of your capacitor bank and voltage regulator, which, if they're optimized, they can not operate as frequently when you have a very volatile variable grid. So I don't want to go through the details here, but I think the main point here is it's a multi-level control system, and with a very strong, secure communication backbone, we can now put applications at the edge that can communicate not only traditionally north-south by having translators from Modbus from a DER system or DMP3 from a capacitor bank or regulator controller. We can also talk east-west between those devices using publish-subscribe protocols that have mutual transport layer security in between them. Additionally, you can even distribute that logic if you want to have more horsepower at the substation, or you want to do an additional layer of analysis at the feeder level. You can do that in a more capable router solution like the A340. And then right now we have a publish-subscribe broker that's allowing a consensus algorithm, meaning the applications running at the edge are essentially working together to really study the system circuit and then kind of converge to a more optimal solution. While this is all happening in seconds, we're still having a DMP3 message back to the traditional SCADA system so that it has situational awareness of how it can coordinate with all this grid edge controls. And I think one more key point here is by having a fleet manager like the field network director, you can push these applications via containers with very little intervention. It can all be done automated in a high scalable fashion and should not require a truck roll if you already have these devices installed on the poles at the control devices. This is just a snapshot of the interoperability. And what we just highlighted here is you kind of have the interaction that is the east-west interaction is a publish-subscribe protocol called NATS. It's using a format, it's open source, called Google Protocol Buffers. And it's essentially leveraging an IEC data model for interoperability based on standards like 61850 and Common Information Model. And then we're converting that between the edge devices like a cap bank to convert from, let's just say, DMP3 into that internal data model. And then the same thing applies for the battery energy storage system. It speaks Modbus Typically, a Modbus device cannot speak to a DMP3 device, and typically even a battery system today does not speak to a distribution management SCADA system. So now we're integrating that into the network, into the operation problem, and we're able now to share data and perform new actions. So I think the kind of highlight, the main things that are unique about edge compute is you can augment your existing north-south traffic, add security, but more importantly, we now can allow that horizontal east-west exchange in seconds or faster on a very strong, resilient, and reliable and available network. And it gives you the ability to add multiple applications. Right now, we're just showing volt-var, but we can even run distributed energy resource applications. We can run different types of optimization for fault detection, demand response. So you can do a lot of these in parallel without having to have a duplicate system. And the key performance indicators, we're just showing that multiple protocols working together within a traditional grid infrastructure and performing use cases that were sub-second. And I think the main ROI here is really the ability to be very non-invasive, targeting troubled circuits. Not every circuit's going to be impacted by DERs. So instead of having to do a full enterprise deployment, you can target those areas that are volatile and need some edge intelligence to complement the DMS. And then from a CapEx perspective, instead of having to invest into multiple assets to provide these capabilities, we can now just put it in the form of software running on a container on the existing telecom infrastructure. So I'm going to next show a grid simulation. This is just to kind of show there's really two major points to kind of take away with the demo. One is the interoperability piece. We're able to get three-phase voltages and provide set points to the legacy devices like cap banks and regulators. And also we're including the energy storage system. And then the second piece is we're leveraging this peer-to-peer communication with a consensus algorithm to quickly converge to a decision on what's the optimal voltage set point strategy. In the demo here, we're mainly going to control a cap bank and a battery energy storage system. So you can just see here, this is a front end of the simulator. We have the live measurements of the grid at the top. We also have measurements of the capacitor bank. This is the actual single line diagram of the topology based on DTE circuit. We imported SIME to build this in the simulator. So you have the battery storage system, the capacitor bank, and the regulator. This is Cisco's Grid Edge Compute UI. You can see we're running those applications for translating between protocols plus the actual coordination app. And it's very easy to package and configure the different containers. We also have the measurements from the CL7 and then the CBC 8000. And then this is the Eaton view. So all three views, Cisco, Eaton, and the simulator are all matching, interoperable. And obviously, they're all operating at a very high resolution. And then we run the consensus algorithm. And this is where the peer-to-peer communication is enabled. And the cap bank now is being turned on to inject reactive power. And then with consensus algorithm, what's going to happen is that it's going to see that the battery energy storage system has some VAR capability, and it's going to essentially kick in to compensate for the cap bank tripping off. So the cap bank, instead of normally a cap bank being used to raise the voltage, in this case the battery is being asked to provide that capability. And normally a battery, which is power electronics, is really made to turn on and off constantly, where a capacitor bank is more of a discrete device which has a limited amount of operations. So there is a lot of benefit to kind of leverage multiple assets. So I believe that completes the grid automation. We'll pass it to Dan, who will kind of introduce the test bed number 2.
Thanks a lot, Stuart. So one thing I wanted to just point out to the audience is that we're going to repeat this talk at 10 o'clock. Then also, we have a booth located on this aisle just right over here where both Stuart, myself, the rest of the team is going to be. So we'll be there running that video demo, and we can happy to discuss in further detail for anybody that stops by. This computer has a life, has a mind of its own. It keeps forwarding these slides. All right, so Stuart covered testbed 1, where we use the model from DTE to simulate the grid, use the edge applications to apply set point adjustments to the controllers. That was testbed 1. The second testbed here, the whole focus was to really drill down on transport of this edge app data over cellular, over macro cellular, and then also over private cellular with bands like Ericsson and CBRS. And we decided to work with a broad range of partners that we've been working with for years, Verizon, Ericsson, and Nokia. Each of the boxes at the bottom, so the red routers were hosted at Verizon's labs in New Jersey. The blue routers in the center were hosted at Ericsson's Plano, Texas labs, and then the light blue on the right at Nokia's labs. The box up at the substation layer, I'll go ahead and point to it here. This was hosted at Eaton in their Pennsylvania labs. And then we did management and orchestration from apps that we had at our Cisco data center. So let me go to each one of these in a little bit more detail to show what the value of the tests were. So at Verizon, if we drill down, we used the router shown on the right there. We used 3 of those. Each of them had 2 modems, which meant that for each router, we could have 2 different cellular uplink types, and we could measure KPIs across those uplinks. So we really wanted to definitely hit CBRS as one of the bands, then also include Verizon's new 5G private offering on bands 66 and 77. And then 5G macro was used extensively between the apps at Eaton and the 2 of the routers at Verizon. So in that case, all of that traffic, it traversed from Pennsylvania to New Jersey, but all of it remained on the Verizon macro network, and we measured KPIs. The other thing worth mentioning is we did north-south traffic between Pennsylvania and New Jersey. We also drilled down on east-west traffic between the routers at New Jersey to see what local routed traffic like that looked like from a KPI perspective. At Ericsson, it was similar, but few important differences. One is we used 2 towers here that had some geographical separation. They were about half a mile apart, roughly a quarter mile apart. And we also focused on Ericsson and CBRS bands. In both the Verizon and the Ericsson case, we used SD-WAN management of our routers. So Cisco software-defined WAN management is something that we've been doing for quite a while. It's a very secure way of managing routers, a very resilient way of managing them at scale, where it's typical to manage many thousands of routers using that. And there's also an app-aware and app management function to that. Shifting gears to Nokia, we did a couple things similar here at Nokia. We did use Ericsson and CBRS. One of the main differences was not only using Nokia's hardware, but also using a different management and orchestration tool that's common in the utility space called Cisco Field Network Director. That also has an extensive app management capability that I'll show you later and that we can demonstrate in our booth. And again, we did both east-west traffic between those routers and the apps on the routers at Nokia, as well as north-south. And what we're going to do next is I'm going to pass the mic to Diana, who's going to talk a little bit more about the cellular systems tested. And then we're going to come back and talk about our cellular results as well as next steps.
Thanks, Dan. Hello, everybody. So this shows, again, the test bed that we had at the Verizon locations. This was in our headquarters, our Baskin Ridge location. In this location, we do have, it's considered like a lab as a service environment. We do have that across the U.S. There's certain hubs that we have in Boston, New Jersey, out in California as well. But again, what we do have here is we had 3 networks actually set up. So we were using the Verizon public network, 4G and 5G. This is actually leveraging a Verizon's private wireless network. So this is an end-to-end private wireless network offering that has, it's leveraging actually Verizon licensed spectrum. As, again, Dan was talking about, we basically had that capability of using our C-band, which is N77 spectrum. So that's basically mid-band. That was also anchored to our LTE, which was band 66 and band 5. So again, we were using different spectrum, also we had CBRS spectrum. So we also have Ericsson. We use the Ericsson EP5G, which is a 5G private network and do 4G, 5G, does also 5G standalone. We had an eNode B, as well as we had a G-Node B. So we had, again, private network. It was actually 5G and also 4G. We have, and we'll show where we covered indoor as well as outdoor. And then we also had set up antennas. You can see here, this is the outdoor antenna to the left. You can actually see, again, the Verizon indoor antennas in the middle there. And then you can see our radio units on the right side. Also, what we leveraged with the private wireless network, we have what we consider a device and SIM management platform that actually integrates directly into what we call our ThingSpace platform. So this is where we have the capability of doing, SIM lifecycle management and also device management through what we call our OSND platform, which stands for On-Site Network Dashboard. And then that dashboard connects directly into the Ericsson network management platform, as well as we offer Nokia as well. So we're tied into the core and RAN platforms for these private networks. And again, you can see some of the test equipment here. This is actually in the lab. You could see where the eNode B is to the left, and then you could see the G-Node B. So those are in the back, sitting on top of that's actually the EP5G core. And then you could see the Cisco 11 IR 1101s. They're running with the Eaton apps. To the left, you could see, again, that's our platform, and that's where we do the SIM and device management. So again, that's our on-site network platform that ties into the private network. Here's the architecture. Again, this is the architecture for the eNode B. The Ericsson EP5G. And then here's Ericsson. We're actually looking at the Ericsson testbed that we have here. As Dan was saying, we had actually 2 eNode Bs, and you could see like an aerial view where there was a core on-premise. There was 2 eNode Bs, as well as we had indoor and outdoor coverage. Here's again Ericsson's test lab where you could see the indoor base stations with the core. And there's Dan, that's out there with one of the engineers, where you could see the outdoor base stations. So you could see how you also have the Cisco dual modem IR 1101s in the right there. And that was in the equipment enclosure that was outdoors. Here's the test bed at Nokia. So this is, you could see again the Cisco routers there. And then on the right, you see the private cellular base station. And again, this shows a little bit more about the Nokia Energy Innovation Center lab that was leveraged. So you could see the private wireless network diagram here. So you could see that they were using, again, different bands. There was Anterix and CBRS. Okay. All right, Dan.
Thanks, Diana. Appreciate that. And so now what we'll do is move to the testing, kind of talk about the test results for our phase 2 test bed, which focused on this cellular transport. And then we also want to talk about the orchestration piece, because doing this on 1 or 2 routers is one thing, but having a system where you can do this with hundreds or thousands of routers gracefully is very important for scaling of this. So for the Ericsson and the Verizon and the Eaton test portions of the test bed, we use Cisco software-defined WAN, and we're looking at here a map view in that dashboard where you can see the routers at Verizon in New Jersey, Eaton in Pennsylvania, and Ericsson down in Texas. And something that's important about having a management solution like this is having a good security architecture and also a stable addressing architecture, something where if you roam or you change modems and you change physical interfaces, you're not changing your application interfaces. So you're not changing your application IP address, I should say. So in all these cases, we had a very good secure overlay-underlay architecture model that we used. The second management and orchestration method that we used is called Field Network Director. This is not a software-defined mode, but it's large scale. It's used today. One of our deployments has 30,000 routers under management using this. It also has app management, and this is the approach that we used for the routers at Nokia. Again, an underlay-overlay architecture, highly secure based on IPsec, also with stable addressing for your SCADA assets and your edge applications. Okay, so by deploying these routers at these 3 facilities, and well, actually 4 facilities, including Eaton, we were able to build up a number of different test topologies. So moving from left to right, we went from the most simple and lowest latency, highest performance on the left, to on the right, higher latency, slightly lower performance. Because the one on the right included transport over internet. If we go to the other extreme on the left, it was a single eNode B, where one of the UEs or routers was connected. The other UE was connected directly to the core by Ethernet. So that's kind of the most direct transport path possible. Moving to topology 2, now we have 2 routers talking through the same base station and the same core. We measured KPIs on that. The third topology is the one at Ericsson we pointed out. So 2 base stations with geographical separation moving through the same core. And then topology 4 is one that we used a lot, where one of the routers was in Pennsylvania at Eaton. The other routers were in New Jersey, and transport was done over the Verizon macro core over a large distance, 500 miles or so. But it didn't leave the Verizon macro core. And then finally, the last example is where you do have 2 separate core networks connected by the internet. So the tested modes that we used, we're looking at these different topologies, also looking at different cellular protocols. We tested 4G and 5G. We tested Anterix, CBRS, private 5G, macro. And in the end, it was 31 distinct UE to UE paths that we have documented. And the types of KPIs we're looking at is what kind of packet loss do we see, what sort of latency and jitter, and then scalability was an important KPI. So this is just a look at the distinct paths. So the types of variations were things like, if we look at use case 3, or topology 3, so it was one router was talking across CBRS at Ericsson, the other across Anterix at Ericsson. So that's an east-west example of 2 routers geographically close to each other. As a comparison, topology 4, that was a router in Verizon on macro, and the second router was at Eaton on macro Verizon. So that's a more distributed, what we called north-south mode. And the ways that we measured the KPI results that I'm going to show you, so software-defined WAN, it has a built-in mechanism where it sends pings and health messages on a periodic basis and reports back latency, jitter, and loss. And one thing that's really nice is you can measure that over very long periods of time and do averaging. So in these results, we use 12-hour averages. You can also do packet tracing and ping tests, which we used. We also deployed the iPerf application on lots of these routers and did iPerf testing as well as just simple ICMP ping. And then we use the router modem itself for cellular quality measurements. So a look at the bidirectional flows. Really the takeaway here is each one of those lines is one of the KPIs, and this is over a 12-hour period. So the top one is loss, the next one is latency, the next one is jitter, the next one is transmission. But by doing that, you can measure an average performance over long, statistically significant periods of time. This is just a tabular view of the same type of measurement. An example of the trace route and pings. So this is a nice trace route showing how many hops there are. We also recorded hops so that it's not necessarily enough to say that from this router to this router, there was this latency. How many network hops did it go through? So that was a parameter that we also documented. And just an example of our iPerf measurements. Okay, so this is the first results slide. This is looking at latency for those 5 topologies that we described. So the topologies are on the top. They line up with the latency result on the bottom. So for example, in that first topology that was very simple, it was 2 to 4 hops. The SNR that we had for all the cellular bands was between 26 and 30 dB for that particular topology. And you see latencies of roughly 35 milliseconds or so. And then going across, you can see how the latency gradually increases. Really, it stays in a pretty tight zone. These are the 12-hour averages that I mentioned. And it's only that you get to the internet where you get a lot more variety because of the non-determinism that comes in with internet routing. But over 31 distinct UE to UE paths, these are the types of latency results that we saw for traffic between the applications. Then if you do a similar exercise for jitter, we got these sorts of results. So the first 4 topologies that did not include the internet, everything was under 10 milliseconds. With the internet, of course, things jumped up a bit. And then finally, the loss measurements. So, we had good, strong SNR. We had good, strong connections, and there was very little loss. So maximum was across the internet at 0.04%. And again, with the loss doesn't mean you lost those packets. It means you lost and retransmitted. So the actual receive rate was 100%, but this is a loss and retransmission state. Last thing I wanted to point out, this has come up a lot in conversations about applications on cellular routers, not just for applications, but also for SCADA assets. And the question is typically, if you're using 2 SIMs, either in the same modem or in 2 modems, and you're changing the IP address of the router, isn't that going to make things complicated for the SCADA master that needs to pull that address, or for a host for an application that needs to reach the Edge application app? And the answer is, yeah, if you're doing all your routing based on underlay network topology, it does get complicated. But if you use a security architecture based on tunneling or based on the typical underlay overlay architectures that we use, the nice thing about that is it abstracts away the underlay. You can have changes in IP addressing on the underlay while keeping constant addressing on your applications and on your SCADA assets. And that's what we always use for our architectures. So this really, if that ever becomes a concern in a deployment of yours, you should just look at doing tunnel overlays, which is going to add security and add stability to the system. Finally, I want to just talk a little bit about, so everything I talked about in this testbed 2 up to now has been really network-based. So it's to show that you can deploy these routers at scale, have a really good secure configuration, a very good robust network transport configuration that's scalable. This looks at the application management on the routers themselves. So SD-WAN is aware of the applications running on the edge. It reports on status of those applications, the Eaton applications in this case. And we're adding, today it doesn't include pushing applications. That's something we're adding in the coming months. However, Field Network Director is the other orchestration tool that we used, and this has for a long time included edge application management. It's kind of like a lightweight vSphere for ESXi, for folks who've ever used that, where it essentially gives you access to the compute space, secure access to the compute space, and it gives you the opportunity to have a library of applications. That's what's on the left there. We've got 5 applications loaded in our library. And then you've got your fleet of routers, and the decision, which of these routers do we want to push which apps to. The other nice thing is from a workflow perspective, it can be scheduled on maintenance windows. You have a lot of insight into router health, application health, et cetera. So this is something that has been done for quite a while and will scale really well for the type of solution that Stuart's team built at Eaton. So with that, I want to wrap up with our conclusions. And before I do that, I want to thank our teammates. So this is a really fantastic team. Working with Stuart and Danny and the folks at Eaton has been wonderful. And same with Diana and her team at Verizon. Kevin Linehan at Ericsson is a great friend and has been great to work with over the years, as well as Mauricio Subieta from Nokia. And then Richard Mueller at DTE has been really helpful. And the great news is, for us, this is really first steps in this project. We're going to mature it. We're going to work with DTE to do some pilot deployments. And this is really, it was a good opportunity to kind of put a lot of focus on it and push the ball forward quickly over the last couple months, but this has a lot of legs and we think we'll get a lot of benefit. So the results are, the question was, can you use edge compute principles to improve smart grid? And the answer is yeah. We showed how you could improve volt-var optimization at a significant level for grid portions that have DER on them and have significant cost savings. The second thing that we want to point out is that edge compute as a software-based approach, all the hardware we've talked about here and the infrastructure, it's existing grid infrastructure. The routers are typically there. The orchestration platforms are there. So we're using software only as a value add to existing grid infrastructure. The last questions were, was the transport reliable over these public and private cellular networks that we tested? You could see from the KPI results, it definitely was. And can it be orchestrated at scale? And yeah, we use tools in this that we have deployed in production for tens of thousands of routers. So that was our last conclusion. And with that, do a time check. We're at 8:45, so we can take questions here. The other thing is the Eaton and the Cisco team will be at the Cisco booth, which is just right over here on this aisle. We'll be here all day. We can answer questions there as well. But since we have time, I'll ask if folks want to bring anything up here. And if so, I could pass you the mic so folks can hear you. Yeah, please.
Thank you for that wonderful presentation. One of the slides that was intriguing was how you showed the performance for latency jitter across different topologies. So we've heard with private 5G and private cellular that you can achieve like sub 10 millisecond latency. Maybe the use case doesn't warranty that kind of latency application, but is it because the core is sitting in the cloud and not on-prem? That's why the latencies were that high to start with?
Thank you. That's a great question. So the reason the latencies were a bit higher than that in this case is if you want to reach the types of latencies you mentioned, you have to use 5G, and it has to be optimized, and you have to use settings to reach those kinds of very low latencies. In these cases, it was typically 4G. So at the Ericsson example that I showed with the 2 base stations, and also at Nokia, those were all 4G technologies. At Verizon, we did use 5G, but we didn't always use it on both ends of the circuit. So I wouldn't really call, although we did test on 5G, this really was not a look at doing low latency 5G. This was more of a 4G testing. Okay, so with that, we'll finish up, but we would welcome you to stop by the booth, and then also, if you don't have time to talk today, stop by, get one of our cards, and we can have a follow-up discussion with you as well. Thank you.